Hi, I'm Tony Heiser with KEB America. I'm the Business Development Manager for Commercial Electric and Hybrid eMobility applications. Today, I'd like to speak about electrifying auxiliaries in commercial vehicles. In this session, we'll examine the benefits of innovative solutions which can be realized with the KEB T6 auxiliary inverter system designed for eMobility applications. Such benefits include reduced components and system complexity and increased auxiliary efficiency, performance, and reliability. Specific topics covering how these benefits can be achieved will include scalable hardware for controlling multiple auxiliaries, advanced motor control including sensorless algorithms, smart control solutions with a focus on electro-hydraulics and servo pump solutions, and tools and support. But before jumping in on these topics, I'd like to provide a brief introduction of the T6 auxiliary inverter product, as well as an overview of KEB as a company to provide some background and put into context our product development and application experience, which has led to our current and expanding eMobility product portfolio. As a brief introduction, the T6 is an inverter designed for commercial electric or hybrid vehicle or mobile machinery applications. The inverter is compatible with high voltage DC supplies between 200 and 820 volts DC. The intended applications are high voltage AC motors for low power auxiliaries of 30 kilowatts or less. These types of auxiliaries typically consist of pumps, compressors, and other direct drive or geared motor applications. Here, all types of AC motors are supported, including induction, permanent magnet, and synchronous reluctance. The T6 auxiliary inverter is a product specifically designed to meet the requirements of commercial vehicle applications. This includes the use of automotive qualified components, E1 markings, CAN J1939 communications, EMC compliance such as meeting ECE R10 standards, design in accordance with shock and vibration for commercial vehicles, and production following automotive industry quality management practices. Now a little bit about KEB. KEB is a leading global manufacturer of industrial control and automation products. The company has manufacturing facilities in Germany, the United States, and China, with sales offices globally. KEB manufactures a full lineup of automation products from touchscreen HMIs down to the motor shaft. Products include HMIs and embedded controls, AC inverters, AC induction and servo motors, including geared motors, and electromechanical clutches and brakes. KEB's market approach is to focus on specific industries and applications. Here, we work with customers to develop products and solutions based on industry-specific needs. Some of the markets and applications KEB focuses on are eMobility, compressors, pumps, and fans, high-speed machinery including turbo compressors and turbo blowers, plastic injection molding machinery, as well as punches and presses where these types of machinery typically utilize hydraulic pumps. There are many other applications where KEB has a strong presence, but I found these to perhaps be the most relevant, potentially pertaining to commercial vehicle applications and auxiliaries. KEB's history of developing inverters goes back to 1985, and the company currently produces more than 150,000 units per year. With KEB's history of inverter product development know-how and experience with applications relevant to vehicle auxiliaries, the company has developed the T6 auxiliary inverter for the eMobility market. Let's start by briefly defining exactly what auxiliaries are. A traditional combustion engine namely provides traction power to the wheels, but the engine also drives a serpentine belt which mechanically powers a number of smaller secondary or auxiliary loads. Commonly, this includes a power steering pump, coolant pump, and AC compressor. With an engine, these auxiliary loads constantly had power available as long as the engine was running. But electric vehicle applications replace a constantly running engine with an electric motor which only produces power when in use, otherwise known as power on demand. Therefore, it becomes necessary to power these auxiliaries independent of the motor, or in the case of hybrid applications, independent of the engine. Thus, the solution is to electrify auxiliaries by driving them with AC motors powered by an inverter. I've discussed some of the benefits of electrifying auxiliaries in a past webinar, and a key point is power on demand, that is, operating the auxiliary when needed and independent of the engine. Power on demand can also lead to increased efficiency, better performance, and less emissions. So what auxiliaries do we want to electrify? The list includes steering pumps, air compressors for brake and suspension systems, as well as compressors for air conditioning, HVAC, and transport refrigeration units, hydraulic system pumps, coolant pumps, fans, fuel cell balance of plant components including turbo compressors, electric PTO, and there are many other items that can be driven with direct drive or geared motors. And what types of vehicles do we want to electrify the auxiliaries on? The list includes both on-highway commercial vehicles and off-highway machinery and equipment. On-highway vehicles include trucks ranging from urban delivery to Class 8 semis, municipal equipment such as refuse trucks and street sweepers, and buses including school, transit, and coach buses. Off-highway equipment includes agricultural machinery such as tractors, as well as implements, construction machinery, and mining equipment. And what any of these vehicles has in common is they all have multiple auxiliaries which can be electrified. And KEB solution is the T6 auxiliary inverter, a scalable and modular system solution. So what do we mean by a system solution? Here I've divided up into the following main categories, which include scalable hardware, flexible motor control options, smart software and system control solutions, and lastly, helpful tools and support. The first topic I'd like to discuss is a hardware platform for supporting multiple auxiliaries. Since a vehicle can have multiple auxiliary loads, the T6 was designed as a scalable and modular system solution. That is, a system can be scaled from a single inverter output unit up to 6 independent inverter outputs. And from a modularity standpoint, there are 3 power rating options for each output stage, which include 7.5 kilowatt, 15 kilowatt, and 30 kilowatt continuous. Thus, a wide variety of applications can be supported from a common platform. And from a system standpoint, there's a single high voltage DC supply connection, single coolant circuit, and single low voltage connection, which also includes the CAN bus. To put this concept into context, let's look at a use case example, in this case, a street sweeper. The starting point for many applications is the chassis, so let's start there. The chassis would typically include a power steering pump and an air compressor for brakes, for example, 4 kilowatt each. Each can be electrified with its own inverter, or each could be electrified individually, but with a multi-axis system. This system can further be scaled to electrify the body equipment, in this case to include hydraulic pump motors. And since the pump motors are generally larger, the modular power stage options can be sized accordingly for each auxiliary. The flexibility of a scalable and modular hardware platform can also be exemplified by taking this use case example further to show a fully electrified vehicle where the hydraulic pump motors are replaced with electric motors for each function. So with that example in mind, why a system solution? There are many potential benefits to consider. First, a system solution provides a flexible and expandable hardware platform to easily support multiple vehicle types and configurations. Such is the case where you may have a chassis with different types of body equipment. Whereas the power steering and air compressor may stay the same for the chassis, there may be various configurations of body equipment or different body equipment altogether. Here, it is easy to scale the number of inverter outputs and likewise size the corresponding inverter output stages accordingly to accommodate additional equipment. The system approach easily supports all combinations of chassis, body, and external equipment. In terms of costs, as the number of inverter output stages in a system is scaled, the marginal cost to add each additional stage continues to go down. That is, a 3-output system does not cost 3 times a single output system. This makes larger, multi-axis systems particularly attractive from a pricing standpoint, even more so when you consider the reduced amount of cabling and other components. In a similar manner, a system solution provides a software platform for implementing multiple auxiliaries as well as multiple types of auxiliaries within a uniform programming environment. This benefits developers and system integrators by easing implementation of various auxiliaries or vehicle configurations and speeding up the development process. In regards to programming, KEB has a free software program called CombiVis. Here, multiple auxiliaries can be managed in a single project, and the software includes easy-to-use wizards for startup and adjustment. Such wizards include an automated motor characterization learn process and CAN communications wizard, which allows for easy drop and drag setup of the telegrams. And the program also includes a very useful digital oscilloscope. Another benefit is that compared to multiple distributed inverter modules, a multi-axis system solution reduces redundant components. These include high voltage DC cabling, DC fuses, plumbing for liquid cooling, and low voltage and CAN wiring harnesses. And reducing the number of system components can have several additional benefits. Shown in the diagram is a comparison of 2 systems consisting of 4 auxiliaries. On the left is a distributed system with individual inverters for each auxiliary. On the right is a multi-axis system solution. As one could see, the multi-axis system is a much simpler and cleaner solution, which would likely be easier to implement and install. In addition to reduced system complexity, less components also reduces total system costs. This can significantly add up and should be especially considered for vehicles with multiple auxiliaries. Eliminating redundant components can also increase system reliability by eliminating potential points of failure. This can also lead to reduced maintenance. Less components can also add up to notable weight savings. A particular benefit is reducing the amount of heavy, high-voltage DC cabling or coolant plumbing. Less components can also reduce vehicle space requirements. In terms of space-saving features, the T6 is an enclosed inverter with an IP67 rating. This allows the inverter to be chassis or remote mounted rather than co-located with the auxiliary. This flexible arrangement can be particularly beneficial when the auxiliaries themselves are located where space may be at a premium, such as under the hood, or difficult to access. The T6 also supports motor connections up to 30 meters. A common concern in regards to the distance between inverter and auxiliary motor is electromagnetic interference, but this was taken into consideration during design of the T6 system. Attention was given to the clamping and shielding of connectors to allow for the longer cable lengths. Additionally, each inverter stage has an integrated DC choke to protect against EMI. A use case example where a remote located auxiliary would be beneficial is the power steering in a bus application. Traditionally, the power steering pump would be located in the engine compartment at the rear of the bus and the hydraulic fluid pipe to the steering rack towards the front of the bus. This arrangement has some drawbacks. The added hydraulic circuit complexity due to the length and connections would have a higher associated pressure drop, requiring more power to run the pump. Additionally, a more complex circuit would pose a higher potential for fluid leaks, and circuits within proximity to the engine heating could pose a fire hazard. On the other hand, the solution would be to locate an electric hydraulic pump towards the front of the bus in closer proximity to the steering box. Here, improvements to the hydraulic system can be realized, and the inverter powering the pump motor can be remotely located as needed elsewhere on the bus. The next topic of discussion is motor control options. The T6 supports all types of AC motors with the same hardware and software platform. This includes induction motors, synchronous permanent magnet and servo motors, and synchronous reluctance motors. The types of control modes supported include velocity or speed control, torque control, and positioning. And all of these motor and control types are supported with sensorless control. So what is sensorless motor control? Before diving into that question, I'd like to provide a brief overview of motor control types. These generally include scalar control and vector or field-oriented control with either encoder feedback or sensorless feedback. Scalar control is also known as open loop or volts per hertz. Here, the inverter outputs a fixed output voltage for a given frequency based on a volts-hertz curve. Since the output voltage is only determined by the speed command rather than the actual power requirements of the load, volts-hertz operation can be less efficient under partial loads. This type of motor control is generally pretty simple and low cost since a motor encoder is not needed. It also only applies to asynchronous motors since the rotor magnetization is induced, whereas synchronous motors need feedback in regards to the rotor position. And lastly, open loop tends to have relatively poor performance since there's no speed or torque control and there's limited torque available at low speeds. On the other hand, there's vector or field-oriented control. This type of control is closed loop and either utilizes encoder feedback or sensorless algorithms. With vector control, there's independent control of both torque and speed. Additionally, the voltage output is optimized based on vector calculations and therefore operates more efficiently according to the actual load requirements. Most notably, though, is that closed-loop systems provide far better speed regulation and torque control, which allow for higher performance and dynamic response. Coming back to the question of what is sensorless, sensorless means vector control without encoder feedback. This eliminates the need for a motor encoder and cabling, which reduces costs as well as eliminates potential point of failure and increases system reliability against factors which an encoder may be susceptible, such as electrical noise, vibration, or temperature. Instead of encoder feedback, sensorless control utilizes an observer motor model based on motor characteristics and utilizes the actual measured motor current and voltage to close the loop, and also creates a virtual rotor position. It should be noted, though, that not all manufacturers' sensorless algorithms are equal. Although a comparison may be difficult to quantify, the key characteristics include the speed control response and the torque control accuracy. In this regard, KEB sensorless closed-loop software is very high performance and comparable to closed-loop systems with an encoder. This is possible due to the very fast processor update rates, accuracy of the motor model, which can be characterized with an easy-to-use motor characterization learn process, and KEB's experience with sensorless know-how dating back to 2005. I should make note, though, that sensorless control has its limitations and is not suitable for all applications. Since the motor model relies on voltage feedback, which is a function of speed, applications involving holding torque at zero speed or continuous operation at less than 1% of motor rated speed are not suggested. In these cases, encoder feedback should be used and is not currently supported by the T6. But Most auxiliaries do not operate under these conditions, and sensorless control is a good candidate for these applications. As a use case example for sensorless control, consider the following power steering application, which compares performance and energy consumption between open loop volts-hertz and sensorless closed loop operation. In the table, we have different driving profiles. In the case of driving straight on, you can see that open loop utilizes 9 amps, whereas the sensorless only uses 4. The difference can be explained by the fact that the pump is not working particularly hard in this scenario, and in the case of open loop, it is simply putting out a fixed power command regardless of the loading situation, whereas the sensorless adjusts accordingly. In the next scenario, the steering is maneuvering a curve. Here, you can see that the load and actual current both rise. In the case of open loop, the actual load is now more in line with the fixed voltage output. The actual load is confirmed by the sensorless output, which appears to be slightly more efficient. Finally, you have the case of butting up against a curb. In the case of open loop, this results in a very high current spike of 20 amps, which could potentially trip a fault on the inverter. On the other hand, the dynamic response of sensorless limits the current overshoot to 10 amps. For that matter, it is also possible with sensorless to set up thresholds at which to limit the current to mitigate spikes and prevent any faults. Electrifying auxiliaries provides new opportunities how these systems can be controlled to provide reduced operating costs through better efficiency, increased performance and productivity, and reduce system complexity. Beyond control of the motor itself, smart solutions utilize innovative inverter functional control features and embedded logic control program solutions. An area which can greatly benefit from such solutions in eMobility applications is hydraulic fluid power systems. Hydraulics are generally used to perform working functions which tend to be larger in power than other auxiliary types. Although favored for high power density, hydraulic systems are notoriously inefficient, and therefore they can significantly affect the electrified equipment's battery charge duration or vehicle's range and have large impacts on operating costs. When it comes to hydraulics, a system generally consists of an input power source, such as the vehicle engine or electric motor, which drives the hydraulic pump and provides fluid power to the loads, which consist of either actuator cylinders for linear motion or hydraulic motors for rotary motion. In terms of control with fluid power, it's all about pressure and flow, where power equals pressure times flow. And in electrohydraulics, where the pump is being driven by an electric motor, pressure corresponds to the torque produced by the motor current, and flow corresponds to the motor speed. While there are various types of hydraulic pumps, this discussion will focus on the two categories of fixed and variable displacement pumps. Here, a comparison will be made outlining the benefits and drawbacks of both types before proposing alternative solutions. A fixed displacement pump has a fixed volume displacement per revolution of the pump. Thus, the flow rate is dictated by the speed of the pump. For an engine or PTO-driven pump, this means that the flow is a function of engine speed. Other applications may utilize an engine-driven generator to power an electric motor at a fixed speed. In either case, there is no direct flow control. Rather, flow is controlled with valves, and pressure is only limited by relief valves. The benefits of a fixed displacement pump are that they are simple, inexpensive, and easy to maintain. Two primary drawbacks are that fixed displacement pumps are constantly running and have no direct flow or pressure control. When the pump is running, the fluid is flowing, which creates friction resulting in heat. The flow also builds pressure and when not put to use, is dissipated at maximum pressure by a relief valve, resulting in wasted energy. Whereas the flow is not directly controlled by the speed of the pump, it can be controlled with flow control valves, but these represent a resistance to fluid flow, which also creates heat. In regards to excess heat, there are several ramifications. The excess heat not only represents wasted energy, but also means more oil and a larger reservoir would be needed to mitigate oil heating and possibly external cooling. These add weight and take up space on the vehicle, as well as adds to the system complexity, which reduces system reliability. With variable displacement pumps, the flow rate and pressure can be changed as the pump operates at a given speed. The benefits of variable displacement pumps is there can be flow and pressure compensated control, which reduces or eliminates the need for valves, and pressure can be held with zero displacement when not in use, which reduces wasted energy and oil heating. The drawbacks are that variable displacement pumps are more expensive and more complex, resulting in potentially increased maintenance and less reliability. A solution to the trade-offs between fixed and variable displacement pumps would be to utilize an inverter to vary the speed of an electric motor driving the pump, that is, a variable speed controlled fixed displacement pump. Inverter control of the pump allows for pressure and/or flow control. The control concept uses feedback from a pressure sensor and the motor speed, which can be sensorless, in PID loops to calculate the output motor speed and torque needed to regulate the set pressure and flow commands. At this type of solution, you can get the benefits of both pump types. That is, variable flow and/or pressure control can be realized with the fixed displacement pump, which is less costly and simpler. And like variable displacement pumps, the direct control reduces or eliminates the need for valves, and pressure can be held at zero displacement, which eliminates wasted energy and reduces oil heating. And lastly, there is no noise when the pump is not in operation. Further benefits include increased performance with the ability to have dynamic, on-the-fly control with accurate pressure and flow control. Another benefit is that the electrified pump is independent and not limited by the engine speed. Thus, full power is available on demand. Additionally, the pump can be sized more efficiently according to the actual load demands rather than oversized based on minimum engine speed. And with an inverter, the direction of the motor can be easily controlled, allowing for bidirectional operation. Here, there's also the possibility of potential energy savings from regenerated energy. And lastly, inverters allow for advanced diagnostics and additional pump protection functionality. A drawback of an electro-hydraulic system is that the power electronics and electric motor can be higher upfront cost. But taking into consideration the various benefits could actually result in a lower total cost of ownership. Another item to consider in electro-hydraulic systems is the type of electric motor used. AC induction motors have generally been the most widely used motor type for years, and for good reason. They're widely available in all power sizes, they're reasonably priced, relatively easy to control, and not difficult to maintain. On the other hand, synchronous permanent magnet motors, otherwise known as servo motors, have been gaining ever-increasing prominence, and for good reason too. Compared with an induction motor, they have very high power density, meaning more power in a smaller package. They are more efficient, especially under partial loads, thus reducing power consumption and operating costs, and they produce less heat. Also, the rotors are low inertia, which allows fast ramp-up to speed response from idle, and better dynamic speed control performance in response to load steps. And the motors generally have a higher overload capacity and a large speed range. Furthermore, there are several servo pump solutions available on the market with integral servo motor and pumping unit in very compact packages. A drawback of servo systems, of course, is upfront cost. Permanent magnets have higher material costs than a squirrel cage iron core rotor. But again, taking into consideration the total cost of ownership, the higher efficiency can have significant payback, and the reduced size and weight of the package can significantly benefit the vehicle design as well. Recall the previous use case example where the bus power steering system was remotely mounted. Well, a servo pump is a frequent solution for this type of application. The compact design and low heating allow servo pumps to be installed in a small compartment at the front of the bus near the steering box. Additionally, the high-performance motor is ideally suited for on-demand power steering control, which coupled with a highly efficient motor can significantly reduce lifetime operational costs or extend vehicle range in terms of less power used. For advanced or proprietary control solutions, the T6 also includes an embedded controller. This allows developers to create custom functionality and value-added, innovative, and smart software solutions for their customers. As a use case example, one such type of application which could easily utilize smart control solutions would be power on-demand steering assist. Power steering makes for a good example because there are several opportunities where condition-based control can be used to reduce energy consumption, such as idle reduction when the steering isn't in use, or speed-dependent control, since the flow and pressure requirements vary drastically based on vehicle speed. Of course, there are many other possibilities and other types of applications which similar ideas could be applied to, and these are just brief examples. And the final topic of today's presentation is tools and support. As mentioned throughout the presentation, KEB's free CombiVis program is an excellent tool to assist in startup and adjustment with easy-to-use wizards and has useful diagnostics and troubleshooting features such as a digital oscilloscope, and TeamViewer is integrated for remote support. And one key feature of the program is the automated motor learn wizard to characterize motors for sensorless operation. Only basic motor nameplate data is generally needed, and the automated process takes 3 to 5 minutes. The link shown below is for a video where this process is part of a startup demonstration. Finally, in regards to support is our applications engineering team at KEB. We have dedicated eMobility teams, which are regionally based in North America, as well as various locations in Europe, for localized support and to address the requirements of the different markets. And we offer assistance at every stage of a project, including design concept, system sizing and selection, startup and commissioning, including on-site support as needed, series production preparation, and technical and after-sales troubleshooting and support. If you have applications you are looking to electrify, please feel free to reach out and we'll be glad to discuss solutions.